All right. So, welcome back, everyone. Before we start today, does anybody have any questions for me? Good. All right. So now we're moving on to my favorite part of this course, which is the last half. I guess I could stop there and say the last half is my favorite half, but yeah.
I have a question. For the midterm next week, what's how much of the material is going to be on it?
So there's 2 sample midterms online, so you can look at those, and it'll be the same breakdown of questions. Yeah.
Actually, I looked through the website last night, but I couldn't see where they are.
I think there's a section on the page that says sample exams. Is that correct? I don't know. Can someone check now? Yeah. Okay. Yeah. Okay. Good. Yeah. So this second half of the course is about probability, which is a topic that's become really central in computer science over the last few decades. So it's the kind of thing that at one point in time you didn't really need to know much of it to be a serious computer scientist, but now it's actually really important. So before we jump right in, though, we'll start with because it's Halloween, or it's getting close to Halloween, we'll start with a scary story. So here's the setup. 3 friends whose names are P1, P2, and P3 go off on a camping trip to an island. It's supposed to be a deserted island. And they have a plan that they're going to go there, and they've brought a special bottle of whiskey with them that they're going to enjoy by the campfire on their first night there. So they go, they set up camp, and then they spend their day doing each of their own things. P1 goes fishing, P2 goes for a hike, and P3 goes for a swim, or so it seems. They come back, sit around the campfire in the evening, open the box with the whiskey, and they find that it's empty. Yes? Dining cryptographers. They're dining. They're about to dine on a bottle of whiskey. They open the bottle of whiskey, and they find that it's empty. So this is a problem. And it's a problem for a couple of reasons. So it means one of 2 things. Either one of them is sneaky and came back during the day and drank all the whiskey and can hold their liquor really well, so you can't tell by looking at them. Or, and this is the really worrisome thing, this deserted island is not so deserted. There's someone else on the island. And they need to figure out which of those 2 cases occurred. Of course, they can't just ask each other, oh, did you drink the whiskey? Did you drink the whiskey? Because nobody will want to admit it. On the other hand, they want to know if somebody drank the whiskey, somebody in this group of 3 people, or if there's this stranger on the island who may come back to chop off their heads later in the night. So maybe they should leave in that case. They want to figure this out. So they want a mechanism where the person who drank the whiskey can admit to it, but remain anonymous. So where someone can somehow say, yes, it was me, I drank the whiskey, but the other 2 don't know who it was. So this is given a fancy name called the dining cryptographers problem. It's also called anonymous broadcasting. And if we think about this naturally for a while, we'll think there are somehow technological solutions to this problem. Like they could each take a scrap of paper and a box, and then each one of them writes on the scrap of paper whether they drank the whiskey or not. They stick it all in the box, and then shuffle the box, and then open it up, and you know, either everybody says no, in which case they better get in their canoe and get off the island, or somebody says yes, in which case they're going to be unhappy with each other and suspicious, but at least their lives aren't in danger. That's one solution, but it requires some technology. It requires a box, and it requires little bits of identical paper and pens, and maybe you can hope that you can't recognize the no person by their mark. So that's not great. And really, this is supposed to be a problem about computers who want to do this. So what you have really is 3 computers. They can communicate with each other in pairs, but so they don't have things like boxes and paper to do this with. Okay. All right. So this problem was posed in the 80s, and a solution for that involves many cryptographers of these people. We'll just look at the case of 3. And in this case, it's a really simple version. One of these 3, we can assume, one of these 3 has a piece of information, a 0 or a 1, that says, no, I didn't do it, or says, yes, I did do it, and they want to tell that, they want to broadcast that to the other 2 without identifying themselves. And so they all agree to perform a protocol together that will allow them to determine whether or not the piece of information is a 1 or a 0, 1 being the good thing, meaning that this person drank the whiskey. All right, so here's the protocol. Step 1, each person picks a random bit, bi in 0, 1. And for now, this is a secret. So I turn around and I toss a coin, and if the coin comes up heads, I have a 0, and if it comes up tails, I have a 1. For now, I'm the only person who knows that. Each of them knows their random bit. Okay? Each PI whispers their random bit to their clockwise neighbor. Okay, so P1 picks a bit B1, P2 picks a bit B2, P3 picks a bit B3, and now P1 whispers to P2, hey, my bit was B1. So what does P2 know at this point? He knows B1 and B2. What does P3 know? Well, P2 whispered his bit to P3, so P3 knows B2 and B3. And P3 whispered his bit to P1, so this one knows B1 and B3. Okay. So far, so good. So each PI does the following. Each PI computes SI is equal to the sum mod 2 of their 2 bits. I'll be really explicit about this. That means that S1 is equal to B1 plus B3 modulo 2. S2 is B1 plus B2. Modulo 2. And S3 is B2 plus B3 modulo 2. This is still stuff they keep secret. Okay? And now it's time for the big reveal. Next, each PI computes a bit TI, and there's two rules, and that depends on whether PI is the whiskey drinker or not. So, if PI drank the whiskey, then TI is equal to SI plus 1 mod 2. Otherwise, PI didn't drink the whiskey. TI is equal to SI. Okay? Five. Each person announces this bit. And so everybody knows these three bits, T1, T2, and T3. So each person computes T1 plus T2 plus T3 mod 2. And the claim T1 plus T2 plus T3 mod 2 equals 1 if and only if someone drank the whiskey. Okay. Or another way of saying it is there is an anonymous broadcaster, PI, who has a special bit that he wants to broadcast. And that bit can be 0 or 1. And when they want to do their broadcast, they put that bit here. So we'll call that thing B. Actually, it could be 0 or 1, but we'll just call it B. So this claim that T1 plus T2 plus T3 mod 2 equals 1 if and only if someone drank the whiskey, that's really claiming that this sum is equal to B. Okay. All right. So this claim is actually easy to prove because it really looks like this. What is this T1 plus T2 plus T3? And from this point on, I'm going to stop writing mod 2 is mod 2. Okay. So T1 plus T2 plus T3, well, that is S1 plus S2 plus S3 plus B, right? So the ones who didn't drink the whiskey announce S1, and the one who may or may not have drank the whiskey announces B, 0 or 1, depending on whether or not they drank it. So that means that the TIs that they see are S1, S2, and S3, but one of them has this B added to it. Okay? But that S1 we saw is B1 plus B3. S2 is B1 plus B2. S3 is B2 plus B3. And then there's still this plus B. And now we should notice that A plus B, where these are bits, mod 2, what does that function look like? Well, if I put in 0 plus 0, I get 0. If I put in 0 plus 1, I get 1. If I put in 1 plus 0, I get 1. And if I put in 1 plus 1, I get 0. So A plus B mod 2 is equal to 0 exactly when A is equal to B. Either they're both 0 or they're both 1. If the two bits are different, then you get a 1 here. What does that mean for this formula? Well, this formula is a whole bunch of bits, and it's all mod 2. So there's a B1 that appears here, and there's a B1 that appears here. So those cancel each other out. There's a B3 here and a B3 here. They cancel each other out. There's a B2 here and a B2 here. They cancel each other out. So in fact, T1 plus T2 plus T3 mod 2 is indeed equal to B. So the bit gets correctly broadcast. Yeah? Yeah. No, the bit that he's telling them is a random bit that he generated from a coin toss. It has nothing to do with whether or not he drank the whiskey. The bit that tells him whether he drank the whiskey is this B here, which is only involved in this computation of TI. Okay. All right, so indeed this correctly broadcasts whether or not one person admitted to drinking the whiskey, but why is it anonymous? Why, if I'm one of the people who didn't drink the whiskey and I see this 1 come up, how does it happen that, how is it that I can't figure out, or how can I prove that I can't figure out what, which of the other 2 people drank the whiskey? Okay. So let's look at this. Suppose I am P2. This is without loss of generality. P2 is just one of the 3. They can all do a similar thing. And I didn't drink the whiskey. So here's what P2 knows. He knows the value B2 because he generated it. That's his random bit. He knows the value B1 because P1 whispered it in his ear. And he knows T1, T2, and T3, as well as anything that they can compute from that, including the value of B. But doesn't know B3. Right? P2 learned from P1 what their person's random bit was. P2 knows what their own random bit was, but there's still this random bit that they don't know. So we have to do a little bit of case analysis here. So here's what case 1 looks like. And this is the case where B1 equals B2. So maybe P1 and P2 both picked 0, or they both picked 1. It doesn't matter. What matters is whether or not they're equal. And that gets further split into two cases. So in case A, you have B3 is equal to B1, which means that it's also equal to B2. Now, player 2 doesn't know if they're in case A, because they don't know the value of B3. But they do know that they're in case 1 because they know B1 equals B2 in this case. Okay, and the other case, the other subcase, is when B3, let's say, is not equal to B1, which means it's also not equal to B2. Okay. So let's see what they see. So in that case, they see T1 well, let's see. If P1 is the drinker, the whiskey drinker, then T1 is equal to S1 plus 1, and T3 is equal to T3 is equal to S2 plus S3. Let's expand each of those things. S1 is B1 plus B2 plus 1. But if B1 equals B2, then this is 1. And T3 is S1 plus S2, so that's, or S2 plus S3, so that's B1 plus B2 plus B2 plus B3 is equal to B2's cancel out, and B3 is equal to B2, so they see a 0. All right. And on the other hand, if P3 drank the whiskey, then the situation is inverted. Then T1 is equal to S1, which is going to be equal to 0, and T3 is equal to S2 plus S3 plus 1 is going to be equal to 1. Okay. That's just because the 1 moved from up here to down here. Okay. So if they're in case 1A, then this is what they will observe. They'll see T1 announce, if P1 was the whiskey drinker, T1 announces 1, and T3 announces 0, or S3 announces 0, and otherwise 0 and 1 if P3 was the whiskey drinker. All right, now let's look at what happens if this B3 is different. Well, in that case, if P1 is the whiskey drinker, then T1 is equal to S1 plus 1 is equal to, this was a mistake. S1 is B3 plus B1. Right? S1 is what this guy announces, P1, that's B3 plus B1. Okay, S1 plus 1 is B3 plus B1 plus 1. B3 and B1 are different, so this is 0. And T3 is S3. Geez, I got many of these things wrong. Sorry. T3 is S3, which is just B2 plus B3 is still equal to 0, because in this case B2 and B3 are equal. In this case it's B3 plus B1. That's still true. All right, so this is S1 plus 1. This is S3. This is S3 is B2 plus B3. B2 and B3 are different. Right? B2 and B3 are different, so that's equal to 1. And finally, if P3 drank the whiskey, then it looks like this. T1 is equal to S1. T3 is equal to S3 plus 1. And these things change. The 1 moves from up here to down here. So this is 1, and this is 0. Okay. So there's a little bit of calculation to do, but let's take a step back and just look at the big picture here. So P2, they know if B1 equals B2, because they know the value of B1 and B2. Okay? So they know if they're in case 1, they know it. On the other hand, they don't know the value of B3, so they don't know if they're in case 1A or they're in case 1B. But look, these cases have exactly opposite outcomes. So if they're in case 1A, then the person who drank the whiskey is the one who outputs the t value that's equal to 1. On the other hand, if they're in case 1B, the person who drank the whiskey is the one who outputs the t value equal to equal to 0. Yeah. So if in this, they learn nothing because whatever they see is completely controlled. It's completely inverted by whether or not B3 is 0 or 1. And they don't know B3, so they can't figure out anything from this case. Okay. Yeah. 1B. So if P1 drank the whiskey, then his T3, so that means P3 didn't, so he's not going to lie. He's going to say his value was S3. His value is S3, which is, if you look over there, that's B2 plus B3. And this is the case, if you're in case B here, B2 and B3 are not the same. So they get a 1. Yep.
For case 1, if we can reverse it, why is T equal to, let's say S2 plus S3?
Where's that? Yeah, no, that's wrong too. That's it's just S3. But so it's still the inverse of what happens here. Here S3 was 0, and here S3 is it should just be S3 plus 1. Yeah, so S3 is 0, so S3 plus 1 is 1. Yep.
Or in the whole casing, do we assume that all the three players are going to tell the truth, or do we consider the fact that
All the three players are going to they're going to execute the protocol correctly. And all three players want, even the one who drank the whiskey wants the other people to know he drank the whiskey because he doesn't want to have to leave the island. So everyone will execute the protocol as it's described. And even the one who drank the whiskey is happy to do that because it gets their information out, and we're just about to finish showing that it does so without identifying them as the one who drank the whiskey. Okay. All right. That was just case 1 where B1 equals B2. There's another case 2 where B1 is not equal to B2. I guess I can do it by erasing things here. So B1 is not equal to B2. And that splits again into 2 cases, which are defined slightly differently. So you could have B1 or B3 is equal to B1, or B3 is equal to B2, right? If B1 and B2 are different, then B3 is either equal to B1 or B3 is equal to B2. And if we go and do this calculation, if P1 drank the whiskey, then they're still going to output S1 plus 1, which is going to be B3 plus B1 plus 1. But that's going to now be 1. B3 and B1 are equal, so that's going to be 1. And T3 is going to output S3, which is B2 plus B3. B2 and B3 are different, so that equals 1, right? Because B3 is equal to B1. It's not equal to B2, so this will output 1. On the other hand, if P3 drank the whiskey and P3 drank the whiskey and the other one didn't, then both of these change to zeros. You evaluate the same thing, and you get zeros instead of ones. And the second case, when B3 equals B2, so if P1 is the whiskey drinker, then it's going to output S1 plus 1. S1 is B3 plus B1. B3 and B1 are different, so that's going to be a 1 plus 1 is 0. And T3 is going to output S3, which is B2 plus B3. In this case, B2 and B3 are the same, so that's a 0. And then down here, they will both output 1s. Okay. Now again, P2 knows B1 and B2, so they recognize, if they're in this case, that B1 and B2 are not equal. On the other hand, they don't know B3, so they don't know if they're in case 2A or case 2B here. And whatever they see is completely inverted by that value of B3, right? So if B3 is equal to B1, then they'll see, if in the case P1 drank the whiskey, then both T1 and T3 are 1. In the case B3 drank it, they're both 0. Opposite down here, if P1 drank the whiskey, they'll both output 0, and here they'll both output 1. So they see something that they knew that somehow this is what they were going to see, either 1, 1 or 0, 0. But which they see depends on what that value of B3 was, which he doesn't know. So indeed, no matter what P2 sees, they don't have a better than 50% chance of figuring out whether it was P1 or P3 that admitted to drinking the whiskey. Okay. Yep.
Something that's a little good is if the B bits are taken random, then how do we create any meaningful information?
Well, I think the point is you can't. In fact, that's what makes it secure. It's that the P2, the one we've been analyzing, what that person sees depends on, or what they can deduce from it depends on this value of B3, which they don't know. And so if B3 is 0, they'll see one thing. If B3 is 1, they'll see exactly the opposite thing. And that means that what they see really has nothing to do with who drank they can't conclude anything about who drank the whiskey because of what they see. Yeah.
In that case, I'm not too sure in which step exactly is whether or not they drank the whiskey.
Right here. So you think of it this way. Each of these guys has 2 bits, one of their own and one that their neighbor gave them. And either they announce it truthfully or they lie about it. And only one lies about it. It's the one who drank the whiskey. They flip that bit. So if nobody flips the bit, then you'll see the outcomes are different and they'll all conclude. In fact, they'll recognize here the output is 0 and they better get off the island because nobody in their group drank the whiskey. On the other hand, exactly if one person drank the whiskey, then they'll flip this bit. This will come out as a 1. But so what they learn is that, yeah, somebody admitted to it, but we don't know who. Yeah.
So what if I'm the one that drank the whiskey and I want to see the outcome of the others? So can we assume?
Well, if you're the one who drank the whiskey, then you don't. You know everything. You know you drank the whiskey, so there's no secret. You know one of the 3 people in the group drank the whiskey. It was you. You can't quite learn the 2 random bits of the others, but you can learn whether or not they were equal, if that helps you. But in fact, yeah. So you can learn if B1 equals B2. And I guess actually you knew B1. So you'll know all the bits in that case. So the person who drank the whiskey in the end knows everything. Yeah.
Do we assume that only one of the 3 drank the whiskey?
Only one of the 3 drank the whiskey. If 2 of them did, then they both admit it, and then we have a bigger problem because this thing comes out as 0, and then they just all run away. But if 2 of them drank the whiskey, then you have 2 of them who know it. So that's not such a big secret anymore. And then there's one dummy who's got 2 really bad friends. Okay. So that was just sort of an interesting curiosity about different ways probability or randomness can be used. And here we see that actually it's used to solve what looks like a problem that at the outset seemed maybe impossible to solve. Like you have a group of computers and you want to know, does one of them have the token without revealing which one has the token? So somehow the one who has this token, the one who drank the whiskey, can tell the others without actually them knowing that that's the one who has it. Yeah. Uh, so you want to play a game of telephone where the whiskey drinker flips the bit. And it depends only on one random bit given by P1. Okay, so the problem there is that at the end of this process, P1 will know if somebody drank the whiskey. Is he gonna say? Then the danger, I think, is the one in the middle. So P2 sees what came from P1. Yeah. Well, yeah, I guess he doesn't know if P1 is lying. I mean, P1, there's also the possibility that P1 drank the whiskey. Yeah. Yeah, I don't know. I'd have to go through the truth tables to figure it out. Because even this is, you see there's some cases to check. And, you know, you have to look at all the cases and what each player sees. It worries me a little bit that it's got this asymmetry that there's one person with all the power. But maybe it works. Okay, so now we get to the unfortunate part of this lecture, which is for the rest of the course we're going to be working with randomization and probability, which is a really powerful, useful notion. We can do all kinds of amazing things with it. But we have to go through some definitions and some examples, because the really important thing to remember is that this probability theory, it's really mathematics that we're doing. In many, many cases, it models things in the real world very well, seems to model them perfectly. But ultimately, it's mathematics, which means there have to be definitions, and we really have to make it clear what it is that we're talking about. Because when you start taking intuition from the real world, it's very easy to make mistakes. And really the only way to ensure that you don't do that is to understand that every step that you make is grounded in some definition or something that's true about the model, not something about the real world. Okay? Because we'll see there's lots of counterintuitive results in probability theory. And so your intuition is not always the best guide. Sometimes you can use it to guess the solution, but then you have to check it carefully. So here come some definitions. A sample space is a non-empty countable set. Now, if you start to get bored from these definitions and sort of easy results, the thing to do is to look back at what we did earlier in the class and realize that almost everything that I'm going to show you today has a counterpart. So we will see things like the principle of inclusion-exclusion. We'll see things like the sum rule. We'll see things like the complement rule for probability, which all have counterparts for cardinality of sets, so computing the sizes of sets. And that's because underlying both these things are these sets. Yep. There'll be a couple of questions about some of this on the midterm. Yes. All right, so that's a sample space. Each element in S is called an outcome. Some people call these things elementary events. and every subset of S is called an event. Okay, so for example, there's a set S which is non-empty and it's countable. In fact, it's finite, so it has 6 elements, so you can count them. 1, 2, 3, 4, 5, 6. 1, for example, is an outcome. On the other hand, 3, 4 is an event. That's all we're saying. Intuitively, we think of this as some experiment happened, and the result of that experiment is one of these things. And so those are the outcomes, possible outcomes of the experiment. And these events are sets of outcomes. Like you can say, I ran the experiment and I got an odd number that corresponds to this event here. 3, 5, 1, 3, or 5. Okay. So far these are just other names for things that we already have seen. A probability function on S is, of course, a function. Usually write it this way. It takes an element of S and gives you something, a real number between 0 and 1, such that and these are really critical. For any element of S, this probability function assigns it a value between 0 and 1. And if we add up for each element of S, so for each outcome, if we're using this new language, we add that up over all the elements in S, then we get 1. Okay. And this PR of W, we say that out loud as the probability that outcome is equal to W. And if you look in the textbook, this thing that I'm calling W is actually an omega in the textbook, but I'll keep forgetting, and so I'll just call it W as I talk here. Okay. All right. And then finally, a probability space is a pair. SPR, where S is a sample space. And PR is a probability function on S. Okay. And if we take any subset A of S, we define the probability of A is just equal to the sum over all of the outcomes in A of the probability of that outcome. Okay. So this probability function really, it takes as input one element from the set S and gives you a number between 0 and 1. But very often it will be convenient. It's hardly ever the case that we're working with individual elements of S. So we'll more often be working with these events, in which case, well, the probability of that event is just the sum of the probabilities of its individual outcomes. So a couple of examples. Imagine I'm trying to model flipping a coin. So a coin that has a head on one side and a tail on the other. Then I might say, well, the set S has two things in it, head and tail. And the probability function maybe looks like this. Probability of heads equals the probability of tails equals what? Yep. 0.5 or 1/2. Okay. So as soon as I tell you that this is the space and the probability of heads equals the probability of tails, but why does that mean that they're both equal to 1/2? Yep. Yeah. And that's because probability of heads, tails is equal to probability of heads plus the probability of tails. But that equals 1 by this rule here, that if I take all the possible outcomes and sum them up, sum up their probabilities, I get 1. So that means if these two things are equal, they must both be equal to 1/2. Here's another example. Flipping a coin twice. So in that case, first flip might come up heads, the second flip also heads, or heads tails, or tails heads, or maybe tails tails. And if I believe, if I have some faith in what this experiment looks like, then maybe I might also say that the probability of getting two heads should be the same as the probability of getting two tails, which should also be the probability of getting a heads and a tails, which should also be the probability of getting tails and heads. And there's 4 of these here, and that's everything in the space. If they're all equal, that means they're all equal to 1/4. Easy stuff. Here's another one. Rolling a 6-sided die twice. So you know what I'm talking about. Here's a a bad picture of one of these things, right? There'll be something like 6 dots. So it's a cube, and on each side of the cube, there's some number of dots. And that dot represents the number of those dots. So really, when we roll one of these things, what we do is we count the number of dots, and that's sort of the outcome that we think of the roll. And I do that twice. I'd roll it the first time, and I roll it the second time. So that means the set S has 2 things. It's a pair of things, an ordered pair of things, I and j. And I and j can be any integer from 1 to 6. So actually, when I roll the same die twice, there's 36 possible outcomes. 6 choices for I, 6 possibilities for the first roll, 6 possibilities for the second roll. And usually in this model, and the model that corresponds pretty well to reality, is the probability of ij is equal to 1 over 36 for all ij. Okay. Questions so far? That's right, it's the standard thing you do in a game of craps. If you're going to play craps, you better understand that probability space very well. So let's consider that one right there, rolling the 6-sided die. So let AK, it's going to be the event, the sum of the 2 rolls is K. So I'll describe it in this language. And so, for example, that means that A4, how do I get a 4 when I roll 2 dice? Well, I can roll a 1 and then a 3. Or I can roll a 2 and a 2. Or I can roll the first one a 3 and the second one a 1. So the probability of A4, which we can interpret as if I roll a die twice, what's the probability that the sum of those 2 rolls is a 4? Well, that's equal to, we can apply this definition. Probability, it's right here. It's the sum of this individual outcomes. The probability of 1, 3 plus the probability of 2, 2 plus the probability of 3, 1 is 1 over 36 plus 1 over 36 plus 1 over 36 is 3 over 36, which is 1 over 12. Okay. Is that clear? 3 possible ways it can happen. Each one happens with probability 1 over 36. All right. Now, that's just one example A4, the probability that I roll a 4, what does the picture look like in general? Well, for that, we can draw a little table and say, you know, here's the value of the first one, here's the value of the second one, what's their sum? So that's going to be so if I roll a 5 on my first roll and a 2 on my second roll, then the value that I get is a 7. Okay. And we said the probability of A4 is equal to 3 over 36. Why was it 3 over 36? Well, because the number 3 the number 4 appears 3 times here. There's the 3, 1, there's the 2, 2, and there's the 1, 3. So, what's the probability of A2? Probability that I roll a 2. Yeah. 1 out of 36. Probability that I roll a 3. 2 out of 36, or 1 out of 18. So that's twice as likely as a 2. 4 we saw was 3 out of 36, or 12th. 5 is going to be 4 out of 36, which is a 9th. 6 is an annoying one because it's 5 out of 36. That's all it is. It's 5 out of 36. 7. 6 out of 36. 1 out of 6. And then we start counting down. Okay, so really important if you play craps is to know this thing, like really know it. So weirdly, the most likely outcome when you roll 2 dice is that they sum up to 7. Something that you don't get until you really understand what's happening here. Okay. All right. So I think this is really important, so we're going to leave it. I'll just change one thing because it's redundant. So it's a function from the outcomes onto real numbers, but these two things mean that they have to be between 0 and 1 anyway. So here's a few things that the book presents, sometimes as lemmas. But here's the most basic one. The probability of the empty set. What's that? Well, we can apply the definition. It's the sum over all the omegas in the empty set of the probability of that thing. But this is an empty sum, right? There's no terms here. So that's 0. So that's an important fact. So here's a definition, which you probably already know. Two events, which are just sets, A and B. You say that they're disjoint if they have nothing in common. So that means in their Venn diagram, you have A and you have B. Nothing in their common intersection. Disjoint, then the probability of A union B equals, well, why don't you tell me? Yep. Yeah. So the way to get probability of A union B is I have to add up the probabilities of all the little events in here and all the little events in here. I have a name for the probabilities of all the little events in here. That's just probability of A. I also have a name for all the little events in here. That's B, and their probability is B, the probability of B. And there's nothing else in there, right? That's A union B. And I think it's not a stretch then to say if A1 through AN are pairwise disjoint, then the probability of A1 union A2 union AN is equal to sum I minus 1 n of the probability of AI. That is just this picture up here, but with a whole bunch of sets. A1, A2, A3, up to AN. And pairwise disjoint here just means AI intersect AJ is the empty set for all I not equal to j. Do these look familiar? Have you seen this rule before? So talks about disjoint sets. Yep. Called the sum rule. And in the sum rule, we were talking about the cardinality. So the size of A union B is the size of A plus the size of B. And the size of A1 union A2 up to AN is equal to the size of A1 plus the size of A2 plus the size of AN, and so on. So these things are actually a generalization of, these two things are a generalization of the sum rule. In fact, cardinalities, sizes of sets, they're almost like a really special kind of probability function where everything has, you can't say that everything has probability 1, but everything has the same probability. Okay. Here's an example, coming back to rolling something, rolling a die twice and taking its sum. The probability that the sum is even when I roll 2 dice. So we have a name for that. So that is, well, if it's even, that means it's 2, 4, 6, 8, 10, or 12. So that's A2 union A4 union A6. 8, 10, 12. Now, can the sum be 4 and also be 8? Can I roll a 4 and an 8 at the same time? No. So that means that this event, which is I roll a 4, and this event are disjoint. I roll an 8. Those are disjoint events. There's nothing that, there's no outcome that is both a 4 and an 8. So that means we can add these, get this thing by adding these up. Anybody know what the answer is? 1/2. Now, was that by intuition or was that by guessing? Intuition. Okay. So, I mean, according to this, we need to really add up all of these things, which would be, we've got a 1 over 36 here, we've got a 3 over 36, we have a 5 over 36, we have a 5 over 36, we have another 3 over 36, and another 1 over 36. And indeed, if you add all that up, you'll see that 6, I got that right, yeah, it's 18 over 36. So it is equal to 1/2, but not so obvious. And also, this is a little bit unsatisfying because this is really a brute force way to do this, right? I mean, what if these were 1,000-sided dice, or even some D&D dice, some 20-sided dice? That would be a bit more work than I wanted to do. So let's see if we could have solved this another way. So, I plus j is even if I is even and j is even, or I is odd, and j is odd. Right? In fact, the mod 2 arithmetic that we were doing earlier relies entirely on that. So if I is even and j is even, I add up two even numbers, I get an even number. And if I is odd and j is odd, I add both of those things up, and I get an even number. So that means probability that I plus j is even is equal to the probability I is odd and j is odd, or I is even, j is even. So I is odd and j is odd. I mean, both of these things can't be true at the same time, right? I and j can't both be even at the same time as I and j both being odd, no matter what values of I and j I take. So that means I really have two events here. Call this one A, in the case where they're both odd, this one B, where they're both even, and those are disjoint events. So that means probability of I is odd, j is odd, plus the probability that I is even and j is even. So this is a bit nicer because there's only two things in our sum. Now, I is odd and j is odd. So I and j are supposed to be outcomes, you know, here and here. How many outcomes are there where I is odd and j is odd? How many choices for I? 3. 1, 3, and 5. How many choices for j? 3. 1, 3, and 5. So that means there's 3 times 3 is 9 possible choices for I and j, and each one of those has probability 1 over 36. So this is 9 over 36. And the same argument here, that their I is even and j is even, gives me another 9 over 36, which is 18 over 36, which is a half. And now we're out of time.